Hi there, this is Electromagnetism lesson 4, and this one is the motor effect and DC motors, which is direct current. So we're going to explain what the motor effect is, and then we're going to apply Fleming's left-hand rule to problems, physics problems, and establish essentially how a DC motor works. So just a bit of information to start with. So magnetic field lines. So we should know now that magnets interact with each other because they've got magnetic fields. And current carrying wires also produce a magnetic field. So we've done that in previous lessons. I'm going to give you some more diagrams. You might have seen these before, you might not. You could be asked in an examination to sketch the magnetic fields between, different orientations or different combinations of magnets. So, if you want to get them down, just pause and sketch them down. All right, let's move on. Right, so the motor effect. So what's this? So if a current carrying wire, which is just a wire with electricity in it, is put into another magnetic field, the two fields interact. That's obvious. We've done the right-hand rule previously. We know that when current passes through a wire, there's a magnetic field associated with it that's either clockwise or anti-clockwise around the wire itself. And if we introduce that into another stationary magnetic field, the two fields will interact and we'll get a force that's produced. So the two fields push on each other, which creates a force on the wire. We call it the motor effect, and it's used inside every electric motor today. So in this instance, we've got a current carrying wire. It's in a magnetic field. It'll move. Once you've learnt Fleming's left-hand rule, you'd be able to predict which way the wire is going to deflect. And as a GIF, just an example of the motor effect. So in this one, we've got a power supply, obviously a battery, we've got a coil of wire. Then we've got a magnet at the bottom. So the electricity passing through the copper wire obviously produces, its own magnetic field, and it interacts with the magnetic field below, and it causes motion, which in essence is the motor effect. A couple of questions then that you can think about. So if you want to pause, what happens when the current is switched on? And what happens when the direction of the current is reversed? So what do you think happens? So when the current is switched on, the motor effect kicks in and the wire experiences a force. What happens if you change the direction of the current? Well, the force will change direction. And this will be established once we go through the left-hand rule. All right, let's do some more. So how do you think we could increase the force on the wire? So think about, the past stuff that we've learnt already. How do you think we could increase the force on this wire that's inside this magnetic field? Well, we could increase the current. That'll increase the force on the wire. And we could increase the amount of wire or turn it into coils instead of a straight line. And that'll also, increase the force, increasing the length, so to speak. Essentially, if you're making coils, you're increasing the length of the wire that's contained within the field, thus increasing the force. Right, so as I said earlier, it is possible to predict the direction of the force acting on the wire, the motion of it. So if the direction of the current or the magnetic field are known, then we can use Fleming's left-hand rule. So here's Fleming's left-hand rule. So you need to get your left hand in this orientation. And then each digit, so your first finger, second finger, and thumb all stand for different things. So the thumb is the motion. So thumb motion. Try and remember it like that if you want. First finger, F for first, magnetic field or field direction. Sec. So it's got a C in it. That stands for current. So you might want to get that down. The magnetic field direction, you might want to draw this on your hand, is always north to south. And the current is positive to negative. Don't write that on your hand before your exam, that's cheating. But while you're learning, feel free to do so. Right, let's move on then. So current direction and 2D page recap. So I talked about this in a previous lesson. So current can be in two directions and needs to be represented on the page. So I asked you to imagine that you're an archer firing a bow. So if you fire a bow away from you, you let go of the arrow, fire an arrow using a bow away from you, you'd see the quill of the arrow. So that means it's going away from you. If an arrow's coming towards you, you'd see the point of the arrow, so a circle. So that's the way of remembering it. So circle means current out of the page. The cross means current into the page. So let's have a look at this one. So You need to get your hand in its left hand position, Fleming's left hand rule. So your thumb, first and second finger all perpendicular at 90 degrees to each other. So it's to start with your first finger on the left hand and point towards south. So you're going north to south. Alright. And then the arrow and the wire. So the current is going into the board because it's cross, or into your iPad or monitor, whatever you're using, or phone. So you have to rotate your arm around. So rotate your left hand, keep your first finger pointing towards south. And then you should see that your first finger is pointing south and your second finger is pointing into the plane of the diagram or into the page. And you'll notice that your thumb should be pointing downwards. Alright, and that's the direction of the force. So a piece of wire would deflect down. That's the motor effect predicted using Fleming's left-hand rule. Alright, I've got 4 questions for you to have a go at. So if you'd like to have a go at these, so you can sketch those diagrams, fill in the missing info, or you could just put your answer on your page and I'll take you through the answers in a second. So remember to pause to do these. Right, so the first one, force direction. So you get your left hand, as we have done for Fleming's left hand rule. North to south, so your first finger should be pointing to the right, and then the current goes into the page. So you have to rotate your hand, and you'll notice that your thumb is pointing downwards, so the force is down. Second one, current direction. So north to south, so you should point your first finger to the left, and then the motion is going down. Alright, so you might need to rotate your hand around, try not to hurt yourself. So north to south, thumb pointing down, and you notice that your middle finger should be pointing towards you. So that'll be a circle for the current direction. North and south poles, so this one you've got current going out of the page and motion going up. So your middle finger should be pointing out of the plane of the diagram and your thumb should be pointing up. And then your first finger will point north to south. Right, last one, force directions. So you can probably predict what's going to happen here. So you've got your north to south, which is left to right. So your first finger should be pointing to the right. And then you've got 2 current directions. So one's out of the page and one's into the page. And you'll notice that one side of this coil will be pointing upwards, force will be going up, and the other one acting downwards. So that'll rotate, that'll have a clockwise turning effect. Alright, hopefully that's okay. If not, you might want to watch that bit again, redo the questions. Right, so next one, when does the motor effect not work? So the field will only interact with the wire if there is a perpendicular component. The more field lines it cuts, the stronger the force. If the wire is parallel, it experiences no force. So, in both of these situations, if you had a wire that cuts at 90 degrees, that'll experience the most force. This one, for example, would still experience a force but less. And this one would still experience a force but even less. If you had a wire that is parallel to the field, so it's acting in the same direction and doesn't cut any field lines, that would experience no force at all. So if it's parallel to the field, it experiences no force. Quite a common question that comes up. Alright, let's move on. So how's it linked to motors? So I want you to predict which direction this will rotate. So for A, so we've got north to south, so your first finger should point to the left. And it's a cross, so it means that the current's going away from you. So your first finger should point to the left and your second finger will point into the plane of the diagram. And your thumb will be pointing upwards, like this. The second one, we've changed the current direction. You might start thinking, oh, well, if you change current direction, that just changes the direction of the force, so it's obviously going down. Correct. If you didn't make that link, north to south, so your first finger points left, current's now out of the page, which means your thumb should be pointing downwards. So this will obviously rotate clockwise. Right, let's have a look at motors then. So what is going to happen in this instance? So if you want to pause and predict which direction this is going to rotate. So a coil of wire carrying a current with rotate, will rotate. That's shocking, sorry. Will rotate due to the forces acting in opposite directions, just like this GIF on the bottom right of the page. So the directions you should have figured out is like this. So this will rotate clockwise. Right, so changing the direction of the force. How do you think we could change the direction of the force? Could do two things: change the direction of the current, so that'd be as simple as switching the battery or power supply around, or we could swap the poles of the magnets. Alright, let's move on. How about the magnitude of the force? Should be straightforward. So how do we change the size of the force? We could increase or decrease the current, or we could simply use a different magnet, either increase or decrease the magnetic field strength. Right, so in the next video I'm actually going to recap this with different types of diagrams, but essentially you really need to know this. Unless the direction of the current is reversed every half turn, so this is in an actual motor, DC motor, like DC motors power electric vehicles, you need to change the current every half turn, otherwise the coil will stop rotating. So what we use is a split ring commutator. I'm actually going to write split ring in there. Split ring. What it does, it's got brushes attached to it so it can disconnect and reconnect. So a device called a split ring commutator is used to momentarily break the circuit, change the direction of the current, and it ensures that your coil turns continuously. Another issue is if you didn't have a split ring commutator and you just had wires, if it was spinning around, wires would get tangled up straight away and it'd be absolutely useless. So brushes, disconnect. The brushes would be located there, either side, and they'd connect and disconnect. I'll go into that in a little bit more detail in the next video as well. Right, let's try an exam question. So we're going to pause and have a go at this one. So the diagram shows apparatus used to demonstrate the motor effect. X is a short length of bare copper wire resting on two other wires. Now the key to this is to realise which way the current is flowing. So remember, current is always positive to negative, so it's actually going to travel that way and then down through this bare copper wire to the black terminal on the other side. So for the wire which we're interested in, the bare copper wire, you need to use Fleming's left-hand rule, north to south. So you need to point your first finger down, and the current is, kind of going down or towards you, and your thumb should be pointing to the right. So what will happen is the bare copper wire will experience the motor effect, and it will deflect to the right-hand side. All right, let's try another one. So if you want to pause and have a go at this. So what difference do you notice if the following changes are made? The magnetic field is reversed. So you should know by now that if you reverse the magnetic field, you would reverse the direction of the force. Or you could just use Fleming's left-hand rule and flip your hand, and you realise, oh yeah, if I change the field direction, my thumb will point in the opposite direction. And current increasing would just increase the amount of force that's experienced. So A, moves in opposite direction, or force reverse, words to that effect. B, faster movement or larger force. So a bit of a longer video that one, but I hope you found it helpful. Thanks for watching, and I'll speak to you soon.